Good morning, everyone. Welcome to the second session of this morning. So before we start the talk, I have a short announcement to make. So after the end of this session, we will have a conference photo in this room, so please do not leave at the end of the talk. So for first talk, we're very glad to have Adam Bouland from Stanford University, who will tell us about the state hidden subgroup problem. So welcome, Adam.
Great. Thank you very much. So today I'm going to be talking about joint work with Tudor, Giurgica-Turon, and John Wright. Tudor should be the one giving the talk, but unfortunately was unable to due to illness. Great. So the problem I'm going to tell you about today is the problem of locating unentanglement. So what's this problem? Let's say we're given a state psi, and it's a tensor product of two smaller states, phi1 and phi2, say on half the number of qubits. But the issue is that you don't know where this state is product. So in other words, you don't know which qubits constitute phi1 and which of the n qubits constitute phi2. So if we draw the states phi1 and phi2 as like colored bubbles representing the fact that they're very themselves entangled, then phi1 could be either qubits 1, 3, 5, and 7, or it could be qubits 1, 2, 3, and 4. Right? And more formally, there's some like bipartition of the qubits into two sets, C and C bar, that of n. And our goal is to find where the state is product, as to say, to find where, to learn this cut between phi1 and phi2. So we call this the hidden cut problem. And the main question we're going to be asking in today's talk is it possible to do this efficiently? That is to say, given polynomially many copies of the state psi, can you tell which qubits are phi1 and which qubits are phi2 in polynomial time? And the answer to this is really not obvious. The reason is that the number of partitions of n into two equal size sets is something that scales exponentially in the number of qubits. And even though you can efficiently check each candidate partition with a few copies via a swap test, this algorithm to locate the cut consumes exponentially many copies of the state and takes exponential time. So this is not an efficient algorithm. So naively, this kind of looks like it could be in like unstructured exponential search problem. Okay. So why are we interested in this problem? Well, the first is that it's kind of a very natural problem in entanglement testing. As I'll discuss on the next slide, it's a generalization of something called multipartite productness testing that had previously been considered in the property testing literature. But the second is that it's also very closely related to quantum pseudo-randomness. Like, if somehow it were exponentially hard to locate where a state is unentangled, then it might give you a new way of, say, combining pseudo-random quantum states by, say, producing two of them and stitching them together across a random cut. Like, if it's hard to locate the cut, it might be hard to tell if a state has this form or not, and that might yield you a form of quantum pseudo-randomness with no entanglement. Right? This is one of the reasons we were interested in this problem. Okay. So to answer this, the first problem we have to ask is this even possible information theoretically? In other words, is there even any information theoretic way of extracting where the cut is located using polynomially many copies of the state? And it turns out that surprisingly the answer is yes. There is a prior work of Harrow, Lin, and Montanaro which showed that you can determine if a state is product across some unknown cut, or epsilon far from any such state, using only order n over epsilon squared copies of the state. So this is kind of solving the decision version of our search problem. This is asking, is the state unentangled? We're asking, where is the state unentangled? And as a warm-up, we've shown this work that we can extend this information theoretic argument to show it is information theoretically possible to find the cut with the same number of copies. So the search problem has the exact same information complexity. And here in our setting, epsilon is how far are phi1 and phi2 from having another cut, like how far are phi1 and phi2 themselves from being product. Okay. And there was a recent result of Jones and Montanaro saying that these are optimal. Like, this is the number of copies that you need up to log factors in order to locate unentanglement. Okay. But what's the issue is that these algorithms, they're beautiful information theoretic results, but they don't yield efficient algorithms. If you wanted to turn them into algorithms, they would be exponential time algorithms. And the intuition is this is kind of like you're performing an exponential number of gentle measurements on your state to test the different cuts. And most of the cuts you test are really far off from the right one, and that doesn't damage the state too much. But this is not an efficient algorithm. This is an exponential time algorithm. So the main question is, can we solve this with polynomially many copies and then polynomial time? Okay. And that's our main result. We actually show that there is a polynomial time quantum algorithm for the hidden cut problem that only consumes polynomially many copies of psi. So this is exponentially faster than the information theoretic algorithms. In fact, the number of copies we use is actually optimal up to log factors by the result of Jones and Montanaro. So we don't need any more copies than they needed info theoretically. And it also works for an arbitrary number of cuts. So if you have a state psi that's a tensor product of a bunch of tinier states phi i's, you're trying to learn some partition of n into m sets that correspond to which ones are which phi I, you can also do that in polynomial time too. Moreover, as an added bonus, our algorithm looks like it's plausibly implementable on a real quantum computer because it parallelizes really nicely and has low depth. I'll discuss this more when I actually show the circuit for solving this problem. Okay. So the way that we find this polytime algorithm is in 3 steps. So the first step is we define a new quantum state version of the hidden subgroup problem, which we call the state HSP. And we show that the hidden cut problem is actually an abelian version of a state HSP. And the relevant abelian group happens to be the group Z2 to the n, i.e. Bit strings where you consider them addition, bitwise addition modulo 2. So this means that this problem is way more structured than a brute force search problem. It has a lot of algebraic structure to it. And then we show that then you can then solve this abelian version of the state hidden subgroup problem using a variant of Simon's algorithm. I think this is really fun because normally when one teaches a quantum computing class, Simon's algorithm is introduced as this very important intellectual precursor to Shor's algorithm, but one that doesn't necessarily have any practical applications. And our result is saying, no, actually, Simon's algorithm is useful. It lets you diagnose the entanglement structure of quantum states. OK. So in order to describe our algorithm, I need to first recap the standard hidden subgroup problem from Mike and Ike. OK, so in the standard HSP, you have some group G and some subgroup H of the group. And you're given access to some function, a classical function f, from the group to some set of labels. And you're promised that this function is constant on the left cosets of the subgroup in G. So in other words, it's constant on the subgroup H. It's also constant on translations of the subgroup H by elements of G. So in other words, this function f obeys a certain symmetry by some action of the subgroup. And your goal is to learn the symmetries of the function, that is to say, learn the subgroup H. And one of the crown jewels of quantum computing theory is that there's an efficient algorithm for this problem in the abelian case that runs in time polylog the order of the group. And this is this thing we learned in Mike and Ike that generalizes Shor's algorithms and Simon's algorithms simultaneously. OK. So in this work, we start by defining a quantum state version of the hidden subgroup problem, which is basically just like the standard hidden subgroup problem. But instead of having a classical function obeying some symmetries, we have a quantum state obeying some symmetries. So in particular, we say our input is a quantum state psi living in, say, a d-dimensional Hilbert space. We get many copies of it. There's, again, a group G and a subgroup H. But we're now given access to an arbitrary representation of the group G on this vector space. So in other words, it's some map from the group to unitary matrices that obeys the group relations. And our promise is that our input state psi is invariant under the action of the subgroup. So what this means is that if you act on the subgroup with the representation of any element of the subgroup H, that stabilizes the state psi. Right? And we also require a second non-triviality condition, which says if you act on the state with something outside of the subgroup, you move the state by at least some amount delta. This is required to make the problem even information theoretically solvable in the first place. Right. And our goal is, given copies of the state psi and the ability to efficiently implement this representation R of the group, to output the subgroup. Now, this generalization of the hidden subgroup problem, I think, could have been defined 20 years ago. It's a very natural generalization of what's happening with coset states to arbitrary representations of a group instead of the regular representation of the group, which is what the standard HSP is formulated in. But the key lemma that makes our whole paper work is that we show that actually this hidden cut problem is a version of the state hidden subgroup problem. And the basic kind of way that we do this is we say, well, let's look at the symmetries of our input state psi, which is a tensor product of two smaller states. And we'll show that if you have many copies of the state psi, that your input states are invariant under the action of actually a few different choices of symmetry groups. And the key step is going to be finding an abelian symmetry group that stabilizes a state, so we can then formulate our entire problem as an abelian state hidden subgroup problem. That's what will yield our efficient algorithm. Okay, so in order to picture this kind of symmetry, it's helpful to draw out what happens if you have t copies of the state. So I'm drawing the copies vertically, and I'm listing the qubits horizontally. I'm assuming, let's imagine the state phi1 is the qubits on the left, and the state phi2 is the qubits on the right. Of course, in the actual problem, you don't know which qubits are left and the right, but it's just a lot easier to picture what's going on if you put them all together. Okay. And the question we're going to ask is, like, what are the symmetries of the state psi tensor T? Well, we know nothing about phi1 and phi2 other than the fact that they're somehow internally entangled. So in general, there are no symmetries of the state within the copies. Like permuting the qubits, say, within phi1, like there's no non-trivial symmetries there. The symmetries that exist in psi tensor T are all symmetries that exist between the different T copies. So let me give you an example. So one of the simplest group actions you can consider on the state is to consider permuting the qubits of the states independently from one another. So let's consider a group that is st to the n. And the way it acts is, so it's a list of n permutations of t elements. And the way it acts is that the ith permutation just permutes the ith qubits of those t copies according to that permutation. So for example, this would be the action of the permutation that cycles the first three elements on qubit 1, and the permutation that cycles the second through the fourth elements on qubit 5, right? And you can actually show that the problem of locating unentanglement is a state hidden subgroup under this permutation group. The reason is there's a really simple to explain invariant subgroup of the state. So if you permute all of the left-hand side states, the cuts on the left-hand side, and the right-hand side independently, kind of like applying one permutation to one and a different permutation to the other, this preserves the state because all those tensor product factors are the same. So this state is invariant under a group which is like 2 copies of ST. And if you knew this subgroup, you would know where the cut is, because where these 2 copies are free from one another, that's exactly your dividing line between the 2 systems. And you can also show that acting with an element outside the group moves the state non-trivially by at least some amount epsilon. This is because you're assuming that the input states phi I are epsilon far from being product themselves. That shows that if you, say, exchange one of the qubits of the states without the others, it doesn't have a big inner product with itself. Okay. So this is great. So hidden cut is a state HSP. But the problem is this is a non-abelian state HSP. We have no idea how to solve non-abelian state HSPs. In fact, you can show that if you apply existing techniques like Fourier sampling over the symmetric group to this problem, it doesn't locate where the cut is unentangled, basically for the same reason Fourier sampling doesn't solve the hidden subgroup problem over Sn. Okay. So how do we get around this issue? Well, we find another group action that's abelian. And this abelian group then allows us to formulate as an abelian version of the state hidden subgroup problem. All right? And in particular, the group that we use is Z2 to the n, that is to say bit strings with addition mod 2. And the way that we define the action of this group, the representation of this group on our states is, okay, first we assume the number of copies of the state is even, and we pair up the copies. So like the first copy is paired to the second copy, third copy is paired to the fourth copy, etc. And what we'll say is if the ith bit of a string x is 1, we're going to apply a swap gate between the ith bit of all of the paired copies. So let me give you an example. So here's the action of 1001, 0001. So this is, this has non-zero entries on the first, fourth, and eighth qubits. So this is saying for each of your paired copies, exchange the first, fourth, and eighth qubits of the copies. And the key point is actually our input state is invariant under a really simple subgroup of these bit strings, namely the subgroup which is like, well, okay, if you don't perturb anything, of course you preserve the state. But if you swap only the left-hand side qubits, that preserves the input state. And if you, if you swap only the right-hand side qubits, it preserves the state. And if you swap all of them, you also preserve the state. So this is a subgroup of order 4 of z2 to the n, where the states is just the group generated by 111110000 and 0000111, where that partition between the zeros and ones is the cut location. And we can also show it moves the state outside of it, so it's also an abelian form of a state HSP. But now we're over a much friendlier group. We're over the group z2 to the n. Okay. Great. So now that we see it's an abelian state HSP, the rest of the algorithm follows more directly. So we know that standard abelian HSPs are efficiently solvable. And in this work, we show that this extends to abelian forms of the state HSP as well. So there's an efficient quantum algorithm to solve any abelian state HSP in time polylog the order of the group and this non-triviality parameter delta. And the proof is basically to consider running some variant of Fourier sampling on your input states, but instead of like this, say you create equal superposition of a group label, perform a controlled group action, and then perform your Fourier transform over your group, and then measure. This is kind of a well-known technique. So like similar circuits also appear, say, in the Bravi et al. Papers and other results studying complexity of Kronecker coefficients and other representation theoretic quantities. But the key lemma that we show is that as you increase the number of copies of your state psi, t, the output distribution of this state Fourier sampling circuit actually converges very rapidly to the output of the corresponding Fourier sampling circuit for the standard HSP algorithm. And that's exactly the thing that lets you solve the standard abelian HSP. And your rate of convergence is exponentially good, something like 1 minus delta to the t. So as long as your non-triviality parameter delta is say, a constant, this is an exponential convergence. You barely need any copies for us to just output exactly what the usual HSP algorithm does. Great. So let's put this all together. I can now give you the circuit for how to locate unentanglement of your quantum state. So in our setting, G is Z2 to the n. And we have this simple hidden subgroup, which is this order 4 subgroup. And the Fourier transform over Z2 to the n is Hadamard's. And our representation of the group is swap operations, right? So what does the actual circuit look like? You just basically Hadamard a bunch of qubits, apply a bunch of C swaps, and then you Hadamard again and measure. And what we show is that if T is big enough, the output of the circuit is exactly what you get from the standard HSP. Well, this is basically Simon's problem. You get a random string Y that is orthogonal to the elements of H mod 2. And just like in Simon's, if you just collect enough samples of these, and with high probability, there'll be a unique two-dimensional subspace spanned by this, and you can find the subspace by Gaussian elimination and thus locate the cut. From this, you can immediately see we generalize to more cuts as well. This is just because this just corresponds to having a bigger subgroup. Like if you have k cuts, it's like a subgroup is order 2 to the k. And we can also make the circuit copy optimal by making a few tweaks that I don't have time to discuss today. OK, great. So I'm now going to wrap up. So what have we seen in this talk? So I've introduced the problem of locating unentanglement, or the hidden cut problem, where the goal is you're given a tensor product state. Your goal is to find which of the qubits constitute phi 1 and which constitute phi 2. And what we did is we found a polytime quantum algorithm for this problem that's exponentially better in time complexity than the prior non-trivial property testing algorithms, all while remaining copy optimal. And how did we do this? We introduced a quantum state version of the hidden subgroup problem, And we showed that it's actually in the Boolean version of this state hidden subgroup problem, and that's what makes it solvable by a variant of Simon's algorithm. And this immediately has some applications, say in quantum crypto, by, for example, we can rule out any pseudo-random quantum state that's unentangled, because if you have any unentangled state, our algorithm can just, in BQP, efficiently locate where it's unentangled. Okay, great. So I'll wrap up with a few open problems. I think one of the most interesting open problems from our work is what happens if we have a slight amount of entanglement between the two halves. So for example, what if we take four Haar random states, phi1, phi2, phi1 prime, phi2 prime, and we superpose them across some cut? So the location of the cut is still uniquely information theoretically defined, because it's the one cut that has Schmidt rank 2 instead of Schmidt rank 4 or more across all of the other cuts. And the thing is, you can run our algorithm, and it will output some random strings y. And those strings y, information theoretically, tell you where the cut is. But if you wanted to locate the cut, it turns out you'd have to solve a bunch of noisy linear equations over f2 to the n, which is kind of saying you would have to solve a variant of the famous learning parodies with noise problem, which we believe is exponentially hard. So a priori, I think it's a really interesting question if this is a computationally hard problem or not. But our current algorithm does not solve this. And second, I think another question is, are there some other applications of the state hidden subgroup problem somewhere else in quantum algorithms or quantum property testing? The notion of having a state that's invariant under some symmetries is kind of a very natural type of problem in physics. There's been a lot of interesting works on complexity of symmetrical problems and things like this. So I think there's a great question if our work will find some other applications out there in quantum info. All right, I'm out of time, so thank you very much. Yeah. Yeah.
Are there questions? There's probably only time for one question. So,
Hello, thank you for the nice talk. So I have a question. In the first and second slides, I think that you showed, you had phi1 and phi2 kind of like having a mutual qubits as well. Does the algorithm can it be extended in that way, or are there any theoretical results
no, so they don't have mutual qubits. So the partition is disjoint. So the phi1 is on one set of qubits, phi2 is on the disjoint set of qubits. And you're assuming think of phi1 and phi2 as being independent Haar random states. So there's no other cut in the state in that setting. Yeah.
Okay, is there any way to extend it to those states as well? What do you think, or?
I'm not sure what you mean by overlapping states. I will say there are more general questions, which are can you diagnose other sorts of entanglement structures with the input state? That's kind of what was one of the open problems I was ending on. But I think that's a more general, interesting question, is given as input a state, diagnose something about the geometry of its entanglement structure. There's a lot more complicated entanglement structures out there than the ones we've considered, right? So I think that's a really nice area for open problems.
Thank you so much.
Yeah, thanks.
So let's thank our speaker again.
Thanks.
Yeah, and the next speaker, please come up to set up the equipment.